Hey guys, this is our lab number 12, and today we're going to talk about foodborne disease outbreaks and give you some guidance about how they are investigated and managed when they're found, and also then a few examples from some ones that have occurred in the last 20 years that are of particular interest. Just to let you know, there will be an assignment associated with these videos, PowerPoint presentations, and that will be posted probably on Tuesday. And so let's jump into outbreaks or how epidemiologists start to identify outbreaks and how they stop them. So there's 13 general steps to outbreak investigation, and they are provided here. I will say that some of them are they're relatively fluid, and of course it depends on kind of what's happening, when it's happening, et cetera, and so on. But really, I would say the major steps to sort of focus on are establishment of the existence of an outbreak. Okay, does it exist? And then sort of trying to systematically determine how many people have been impacted, come up with some hypotheses as to what might have happened, conduct the necessary investigation to prove that hypothesis, come up with different hypotheses, reevaluate the hypothesis, et cetera, and so on. And all of that involves kind of a combination of laboratory environmental studies with the epidemiology, and then to figure out exactly how it occurred, which is kind of really where the food safety folks come into, and then to make sure that it stops and hopefully doesn't occur again. So before I launch into all of these, I just want you to understand that the term epidemiology has a very distinct definition, and that is the study of the patterns of disease in populations. Okay, so in the case of humans, it's the study of the patterns and also the incidence, or how frequently it occurs in human populations for humans. But you can do that in animal populations. There's animal epidemiology. You can even do that in plant populations. So in this case, what we're really interested in looking at the patterns and the incidence of diseases that are associated with foodborne routes of transmission. So in the first steps, really, we have to establish the existence of an outbreak. In other words, is an outbreak occurring? And a general definition of an outbreak is two or more illnesses that have some sort of a association by time, place, or person, or two or more of those even. And in the case of foodborne outbreaks, they also have a link to consumption of food. There's an exception to that rule, and that exception is Clostridium botulinum. So a single case of Clostridium botulinum actually is formally identified as an outbreak. But pretty much every other illness out there in the foodborne realm, you have to have two or more cases. How do you establish it, or how do you find it? Well, there's lots of different ways. One way might be from talking to or from reports that get called into public health officials. Another might be through the PulseNet program at CDC, which we talk a little bit about in some of the other slides, and I'm assuming you've spoken about in lecture class. Sometimes there are states that recognize a pattern of illnesses that have been reported to their public health folks. In general, the CDC, which is the federal body that does epidemiological investigation, doesn't usually get involved in outbreak investigation unless there are individuals that are sick in more than one state, so 2 or more states. Usually, if it's limited to a single state, then it's investigated by state public health folks. So let's say you've identified an outbreak, okay, or what you think is an outbreak. And the next step is really to try to find out if you've identified all the cases. Have you found everybody that is a part of this outbreak? And there's a variety of things that you have to do to identify the cases. And the very first thing you have to do is to verify the diagnosis. In other words, what is going to allow us to say definitively this person is infected with this agent. And the second is to construct a working case definition. And the working case definition is a series of inclusion and exclusion criteria that allow you to say, yeah, we are going to include this person because they have these symptoms or this diagnosis or et cetera, so on. And we would exclude them if the following things happened. You know, they had an underlying disease that gave them gastroenteritis anyway, for example. Those are necessary to then move on to the fifth step, which is to systematically look for new cases and to record that information. Now, for multi-state outbreaks where the CDC gets involved, that's relatively straightforward because most of the diseases are reportable. So public health officials in the states are required to report that disease to the CDC, frequently to produce a pulse field gel electrophoresis pattern. And the CDC is doing a process all the time called surveillance, where they're actually monitoring that data and looking for patterns and trends. It gets much more complicated for diseases that aren't reportable, like norovirus is a great example of a non-reportable disease, so we don't necessarily have good epi for it. Or if it's an outbreak that has occurred in a state where you're much more reliant on either individuals calling in or the state public health people being aware that there's a problem. And in point of fact, the states are many of the states in the United States have experienced pretty dramatic reductions in workforce over the last 10 years. And so for less severe outbreaks, particularly norovirus, they tend to be a little reluctant to, or not reluctant, but they tend to not have enough people to investigate those. So those will frequently go uninvestigated. So the next step is to perform what's called descriptive epidemiology. Okay, so descriptive is exactly what it is. It's describing the situation, but it doesn't usually have a quantitative component to it. And really, that characterizes the outbreak from the perspective of time, place, and person. In other words, were the sick people in some way related to one another in time? Were they all kind of exposed at the same time? And or place? Were they all kind of at the same place at the same time? Were they at a wedding? Were they at a restaurant over a certain night, et cetera, so on? Or person? Person being, were they associated with a particular group of people at a particular, let's say a group of family or a church gathering or something like that. And that information allows you then to start to develop hypotheses about how somebody might have gotten sick. So think about our current situation with COVID right now. that people are largely getting sick by person-to-person routes. Okay, so there would be a strong person association. People who ate at the same restaurant or the same event would have more of a food type of association, so maybe a food transmission route. It also allows you to make hypotheses about the source, so where that contamination or where that contamination or where that contaminated food might have come from. And certainly population at risk, okay? And we all know that for certain diseases, there clearly are at-risk populations. And that will manifest itself in are there some similarities in the populations that seem to be affected by the illness? You know, is it largely hitting elderly people? Is it largely hitting little kids? Are pregnant, you know, are we seeing a lot of pregnant women? That sort of thing. And the temporal aspects, so the time-based aspects, once you've identified all of your ill individuals, or what you think are all of your ill individuals, you then describe your epidemic in a temporal manner. Temporal means time, okay? So there are different ways to do this. This is called an epidemic curve. But generally, you have on the x-axis the day of onset of illness. In other words, when that person was diagnosed with, or not, excuse me, when the person showed the first symptoms of illness. And then on the y-axis, you'll have number of cases. And you'll get curves that look something like this. And actually, the pattern or the shape of the curve can tell you a lot about the epidemic, just even from a very basic standpoint. So if you look at the top left curve, that's what we call a point source or a common source epidemic curve. And you see here that the illnesses start and they peak and then they fall almost as rapidly as they peak, okay? And what that means, and usually there's a relatively tight range in here, and this tight range here usually is approximately the incubation period of the disease. And this occurs when a group of people have been exposed to a common source of contaminated food. So they all ate at the same wedding, or they all had dinner at the same restaurant over a period of a couple of days, something like that. If you look at the top right curve, this is called a continuous exposure curve. And what you usually see is a slow and then a more rapid increase in cases. And then those cases will flatten out over a period of time. And once the outbreak is identified and put under control, it will then go down, usually pretty rapidly. This is the kind of thing you see when you have a product that's on the shelf for a long time that's contaminated. And so you continue to have cases occurring over an extended period of time, let's say over the shelf life of that product, until somebody figures out that something's going on. They figure out that it's that food, and then that food is withdrawn from the market, or else has simply entirely been consumed. The last type of design or epicurve is a propagated curve. And this occurs when there's an initial case or initial set of cases, and then you get these waves like this, okay? And what the waves generally indicate is that what the first part of the curve generally indicates is that you have some sort of a common source that's caused a few people to get ill, okay? And then those people will pass the illness on to others, who will pass the illness on to others, who will pass the illness on to others, and so on and so forth. So propagated epicurves usually occur when there is also a person-to-person aspect to the transmission of the illness. So a great example of this might be hepatitis A, that let's say somebody gets or a group of people get ill because of consuming contaminated product. Well, actually, noro is a better example. A group of people get ill from consuming contaminated food, which would be down here. But because norovirus is so transmissible from person to person, it can then be easily propagated through families or through schools or through any type of living situations or working situations where people are in tight quarters. So anyway, the epicurve is telling you something about how this is happening and the type of epidemic you might be dealing with. So you certainly will investigate place. Okay, where did the outbreak occur? Are there any clusters or patterns of cases within the location that the outbreak occurred? That's very important, particularly if there's a common exposure in a regional or a very localized area. Some of the person types of aspects that you might be interested in looking at are features that impact susceptibility to the disease and or the opportunity for exposure. So susceptibility is it can be largely affected by age, it can be affected by gender, race, medical status, socioeconomic status. There's a whole group of features that are important in susceptibility. Opportunities for exposure are frequently based on things like, is everybody working at a common place? Or are there similar leisure activities? Are there medications that people are exposed to? Is this a population that abuses drugs or tobacco or alcohol, et cetera, and so on? So those are the kinds of things that we look at when we're looking for person exposures, or person aspects. So based on time, place, and person, okay, the epidemiologist will then come up with hypothesis generation. And basically they'll say, okay, we think this happened because this group of people were exposed in this venue at this time to a food, let's say, okay, since we're talking foodborne. And that's their hypothesis, but they don't have proof of that. So then they move forward to develop proof for that, okay? And that is generally done by a series of questionnaires. So they will go to people who have gotten sick and try to get a history of, not only a history of their, of their personal features, age, gender, race, etc., but also of their potential exposures, and also some of the timing of and place associations. And those are usually done with very refined survey tools, and they're almost, well, not all now because of the internet, but frequently they're done in person. So an epidemiologist will actually come to that person. But good scientists that we are, you can get all the information you want from the ill people, but you still have to have a control group to compare them to. And that leads to the concept of analytical epidemiology. In other words, how can we prove the hypothesis, almost always quantitatively, using statistical tools in a way that's scientifically valid. And the whole purpose of analytical epidemiology is to make these associations between exposure and disease in a scientifically rigorous manner. Now, there's many different tools to analytical epidemiology, but the two most often tools that are used in foodborne disease work are case control studies and retrospective cohort studies. So in a case control study, you identify people with the disease. In other words, let's say it's an illness that started in a restaurant. You'll identify the people who got sick in that restaurant. And then you will also identify people who were maybe dining partners or ate at another table or whatever, but at the same time, who did not get sick. And those are your controls. So you have cases, the people who are sick, and controls who are matched to those cases, who have a similar exposure, time, place, person, etc., but did not get sick. And then you ask both groups the same series of questions about their possible exposures. This is done very frequently in common outbreaks studies, where you have a common food source that caused the illness. And what you can get out of case control studies is a very defined measure of risk, okay, that's called the relative risk. Retrospective cohort studies are where you actually look at exposure in the past in relationship to a disease that has already happened. So let's say you're interested in risk factors for listeriosis. You would take listeria patients, okay, and look for their exposures prior to getting sick. Retrospective cohort studies are useful when the population at risk is quite well defined. So if you have passengers on a cruise ship, for example, I'm not going to spend a lot of time talking about that in this presentation, because almost all of what we do are case control studies, at least in foodborne. So in case control studies, we calculate something called an odds ratio. And an odds ratio quantifies the relationship between the exposure and the disease. So really what you do is you ask your cases and your controls questions about their exposures. And you then will quantify up how the cases compare to the controls relative to that exposure. So, for example, you develop something called a 2x2 table here, which is the exposure variable versus the response variable being the illness. And you look for the proportion of your cases, which would be your response variable, okay, who were exposed, let's say, to a certain food, and those who were unexposed had not eaten that food. And your controls, you would look at the proportion who had eaten that food, and the proportion who had not eaten that food. And what you get is an odds ratio that is calculated this way. And I'm going to correct something I just said, which is that this is actually not a direct measure of risk. This is an indirect measure of risk. And the way that you interpret this is that the odds of exposure. Okay, so let's say you have an odds ratio of 5. Okay, the cases are 5 times more likely to have been exposed to food X than the controls. And the general rule of thumb is if the odds ratio is 1 or below, there isn't usually a statistically significant association between the consumption of that food and the illness. If the odds ratio exceeds 1 and does not include 1 in the confidence interval, then you do have a statistically significant association between the odds of exposure to that food and that illness. Okay, the higher the odds ratio, the stronger the association. So if the cases are 5 times more likely to have been exposed to food X than the controls, that's a pretty good, that's a pretty good association. But if it's 15 times more likely to have been exposed to that food than the controls, that's a much stronger association. So the higher that odds ratio number, the stronger that association. In retrospective cohort studies, which I really don't think I'm going to spend a lot of time on, we actually define risk as a risk ratio. And if you want to get more information on that, there are some links at the end of this presentation on some EPI classes you can take online through the CDC or I think through UNC as well. But this is less relevant to kind of our day-to-day food safety workings. So usually what happens is once the epidemiologists identify the food, okay, by that odds ratio, usually the food or foods having the highest odds ratio are the ones that are most suspicious. Then regulatory agencies, whether that's in the state or whether that's in at the federal level, will then go in and try to figure out, number one, is it credible that it's this food, okay? And number two, is there some kind of proof that this food was contaminated to basically support the epidemiological results. And this is usually done through lab data, so through testing. Okay, they might go in and they may test or they may sample some of the product that they think was implicated and take it to the lab and test for whatever the infectious agent is. Let's say it's salmonella. Or sometimes they may go in and do environmental studies, look for the presence of environmental contamination in a plant. Let's say this is done frequently in listeria investigations, where since listeria is a known environmental contaminant, is there evidence that there's listeria in that plant? Now, in point of fact, a lot of times we'll link the lab data or the environmental data to even more sophisticated micro methods such as pulsed-field gel electrophoresis, etc. And it's also important to note that just because you get a sample and you get a negative doesn't necessarily mean the epidemiology is wrong or insufficient. And the reason for that is because, number one, depending on the pathogen, lab testing is easier or harder, more accurate or less accurate. But there's lots of other reasons. Remember from our discussions, pathogens tend to be distributed in foods in an irregular or a non-uniform manner. So maybe the sample you pulled out just didn't have the pathogen in it. Or the pathogen died, or the food was all consumed before you could get a good sample, or the environmental investigation happened long after the cross-contamination event happened. So we can't always confirm, but we do the best we can. And this whole process is very, 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 very rigorous to try to kind of look at all the different angles that could have caused the product to become contaminated. And then we move on to implementing prevention and control strategies. And of course, that totally depends on the contaminant and how that contaminant entered the food supply. The major control is once you figure out that this particular food was the likely cause of disease, whether you have laboratory data to support that or not, epidemiological data is usually sufficient. We pull it off the market. So we will initiate recalls to make sure nobody else gets sick. If it's associated with environmental contamination, then there will be thorough sanitizing. There will usually be environmental sampling blitzes to make sure that persistent pathogens are effectively removed from an environment. Certainly for organisms like the enteric viruses that are transmitted largely from contaminated humans, you will enhance your hygiene and training practices. Sometimes you'll provide prophylaxis. This happens with Hep A outbreaks all the time. If somebody is exposed to hepatitis A, let's say from eating in a restaurant, there will be these massive campaigns to get all of the people who had eaten at that restaurant in for vaccination to prevent them from getting sick if they were indeed exposed to that agent. At the federal level, really more than the state, we want to then make sure that these prevention and control measures are working. And this can be done through what's called epidemiological surveillance. And there's many ways of doing surveillance. The bottom line is surveillance has to do with tracking cases and outbreaks over time. A really good example is the National Outbreak Reporting System, where the states are supposed to report outbreaks of foodborne disease to the CDC. Unfortunately, it's not required, so there's wide disparity between, what states do it and what states don't do it, and to what degree they do it. But suffice it to say that we want to make sure that any controls we've put into place will work and are working and are continuing to be followed and are controlling future disease. And then the last thing I want to talk about is communicating findings. This is a really sensitive topic and not one that we talk a lot in this class about. But in point of fact, the public has a right to know. And so when it's a federal investigation, like the CDC does, they will actually formally report their findings, both to the press, in press briefings, and also on the internet. And usually there are some sort of final reports that are issued by the CDC and usually FDA or USDA if they're involved in the outbreak investigation. Another aspect to communication that's incredibly important is how a company communicates an outbreak to its potential customers. And that is a very sensitive topic, and there's a whole science behind what's the appropriate way to do that, such that the public understands without ruining the reputation of the industry, And people like Dr. Ben Chapman, who some of you guys may know, is, works in that kind of communication realm, sometimes with companies. But I can't stress enough the fact that this communication piece is really, really important. People need to know, and they need to be given the right information at the appropriate level with the appropriate degree of understanding, um, and kindness. And I think with that, I am going to show you for further reference. These are some online types of classes you can take if you're interested. Um, and um, and what follows now are examples of 3 different outbreaks that were fairly high profile in the United States that have occurred over the years. I'm sure that over the course of your growing up years, you can think of others. And your assignment is going to focus on looking at another outbreak, which I'll identify and post probably on Tuesday. So be safe, and thanks for joining. And I look forward to seeing your assignments at the end of the week or early next week. Bye.